Okay, so we're in section 14.5, curvature and normal vectors. I thought it would behoove us to take a few minutes here at the beginning to kind of review what we've been talking about this week so far, because there's a lot of formulas and concepts running around. First thing is on Monday we talked about arc length. Okay, so we talked about arc length. Arc length is the length of the curve. We can get arc length by integrating the arc length differential. And the arc length differential, how far you've gone, is going to be found by integrating your speed. And so if I take the derivative of arc length with respect to time, not surprisingly, we get your speed. Because if you think of arc length as distance, traveling so many miles, time being hours, then the derivative, miles per hour, is exactly your speed. Okay, so this is what we talked about on Monday. All right. Then on Tuesday, we started doing some more in-depth analysis talking about motion in space. So to kind of remind ourselves what we've got going on here, we've got a vector-valued function r, which is our position function. And if I take the derivative, the first derivative of r, this is going to give us our what? So the derivative of the position is the what function? Yeah, that's our velocity. That's going to be v. That's our velocity. And we've already talked about the magnitude of velocity, which is our speed. And the direction of velocity, that's aka t hat. That's our principal unit tangent vector. So that's the direction we're going. Now if we take the second derivative of position, which is the first derivative of velocity, what's that called? Yeah, it's called our acceleration. Okay. So we had a big theorem that said that the acceleration breaks down into a tangential piece and a normal piece. All right, so n hat was defined to be the principal unit normal vector. We defined n hat as the derivative of t hat divided by the magnitude of t hat prime. And so once again, t hat prime, t hat is the direction you're going. T hat prime is the direction you're turning. So if I think of a curve in space, and then I'm at a particular point, t hat is the direction you're going, n hat is the direction you're turning, and since t hat is a unit vector, its derivative is orthogonal to itself, which means that these are 90 degrees, they're a right angle, and they are unit vectors. All right? So this says that the entire motion of this object is determined or lives in the plane determined by t hat and n hat, and this plane is called the osculating plane. So the osculating plane this is the plane of motion. And we did an example of t hat and n hat in the osculating plane on GeoGebra, so you can see all that happen. And on your next take home, you're going to have an opportunity to do that as well. So t hat and n hat are orthogonal unit vectors. We define b hat, the binormal vector, to be t hat cross n hat. And so b hat is the this is the normal vector to the osculating plane. And with properties of cross product, since t hat and n hat are both unit vectors that are orthogonal, then b hat ends up being a unit vector. And we have the TNB frame, which is like a portable IJK frame. But it's sort of a 3D coordinate system that follows the particle through. All right, so this is, there's a nice picture of the TNB frame as you're moving through things. Okay. All right, now, the formulas for the AT and the AN, there are a lot of those. So AT, when we derived it, AT, the tangential acceleration, that's the derivative of the speed. So depending on what you're given in a problem, this might be the best way to get the tangential acceleration. But we also went through a proof yesterday using this equation. You can take the dot product of both sides with t hat. The t hat dot t hat would give you 1 because t hat's a unit vector. The t hat dot n hat would give you 0 because they're orthogonal, and you can get AT that way. So literally, how much of the acceleration is in the t hat direction? T hat, though, is the velocity divided by the speed. So you could use properties of dot product to get you to here, or you could write it this way because dot product's commutative. So this is usually a popular formula depending on what you're given. This is also usually a popular formula for the tangential component. AN. When we went through the definition, AN was the speed times how fast you were changing direction. So that's your centripetal component of acceleration. If you're taking a turn and you feel a tug, that's the tug that you're feeling is from this component of acceleration. So it's how fast you're going times how fast you're turning, or how fast you're changing direction, I should say. So you could go through and take the dot product of this equation of both sides with respect to n hat, and the t hat dot n hat would zero out once again because of orthogonality. This would go to 1. So you could get, the classic how much of acceleration is in n hat's direction. But you could go in and you could do cross products. So you could take the cross product of this. And you could get to this formula, V cross A. The magnitude of V cross A over the speed. And this is typically, I think this is the one we used yesterday. Usually you can get the velocity acceleration pretty quickly. You get the cross product, do that. Yeah, the one you used. Yeah, okay. But there is another one that's on the sheet. We didn't really mention it yesterday because I wanted to kind of have a day to have this equation in your head. But you can also look at it as the square root. So this might help you, Derek. It also works out to be this way. All right. Now, does this thing remind you of anything? Like you're taking the difference of squares and taking the square root? What theorem does that remind you of? Yeah, Pythagorean. And here's the reason. You've got A is AT t hat plus AN n hat. So if you think about it, t hat and n hat are at right angles. Right? And so if A is AT t hat plus an n hat, I could just copy this over here using the old vector arithmetic we talked about. Then that would be the vector A. So if I went and just turned this into a triangle, here's the triangle we've got. The length of this side, well, the length of t hat is 1, so this is just going to be our, I guess technically, absolute value of AT. The length here would be the length of this. N hat is a unit vector, so it's just going to be AN. And we don't need absolute values around AN, remember, because AN is already always positive because it's the product of two magnitudes. And this would be A here. So once again, because of orthogonality, A squared plus B squared is C squared. So we can drop the absolute value since we're squaring stuff anyway. So that's where this comes from. It's literally Pythagorean theorem. So Derek, this might be, you might want to go through and try this one. You follow? And see if you can get it to work out. Okay, so then yesterday we defined curvature. And I do like having this class in these little 45-minute chunks or whatever it is. But the thing that you lose is there are some topics where I think you benefit from being able to meet for like an hour and a half or an hour and 15 minutes. And this is one of them because you kind of lose this continuity here. We defined curvature. Curvature, the definition of curvature is we looked at the rate of change of t hat with respect to arc length, and we looked at that magnitude. So remember, t hat is the direction you're going, and s is your arc length. That's how far you've traveled. So you're looking at the rate of change of direction with respect to the distance you travel and taking the magnitude of that. All right. So if you change direction often over a small amount of arc length, the curvature is going to be high. Whereas if you don't change direction too much over a stretch, the curvature is going to be low. So once again, this is like driving on, blasting down I-90 and then coming up to an interchange. Okay. Now, as we talked about on Monday, getting that arc length parameter to work out isn't so bad if you have something with like a constant speed. But if you have anything else, even the parabolic trajectory, trying to figure out that arc length parameter is going to be a pain. So we use the chain rule to get us curvature if we're using any other parameter, say t, instead, some sort of time parameter instead of arc length. And so this was just a consequence of the chain rule there. And then this opened up connections between the curvature and other things. So for example, this meant that the magnitude t hat prime is the curvature times the speed. And so going back to my normal component, I can now express this in terms of the curvature, which makes sense because both of them have to do with how fast you're changing your direction. So my AN, which we got, was the speed times t hat prime. I can substitute this in. This would be the speed times the curvature times the speed, which would be that. Okay. And then finally, to wrap up where we kind of ended yesterday, remember the speed is the ds dt. The tangential component of acceleration is the derivative of the speed. So that would be the derivative of that, which would be the second derivative. Whoops. And then the normal component would be the curvature times this. And so this is what I was remarking about. And once again, I know folks, I think mentor class ends at 9:05. I don't know when all your classes end, but I think mentors ends at 9. Someone's ends at 9:05 or something. That's why the class ends at 9:05. But I looked up at the clock and it was like 9:06 or 9:07 yesterday. So I just find this interesting. Mentor, okay, yeah. So I just wanted to take a few minutes here at the beginning. I think hopefully it was beneficial to walk through all these formulas again to kind of see how they were connected. But this just fascinates me, and I know Rick did a lot of work in physics, but you've got the tangential component of acceleration. That's the second derivative of your odometer, essentially. That makes sense. And then here we've got this calculus quadratic thing, meaning we've taken the derivative twice. Here we're taking this thing and we're squaring it, so it's an algebraic quadratic thing. I don't know. I think that's just interesting that's what pops into that formula. And so that's what gets us to this formula here that we ended with yesterday. So hopefully that was kind of it's just an easier way to get through all these formulas, right? And this is why, folks, that I don't like to give a test on this stuff. I like to make it a take-home so you have time to look through all the different various versions of these formulas and select the one that's going to be the one you can do. The last thing I want to mention about this formula before we move on is that once again, unless you're in a very specialized case, like if you're in 2 dimensions, or if you've got a constant speed thing like a helix, finding n hat using the definition of t hat prime over the magnitude of t hat prime, this can be a mess. Okay, this can be a mess. On the other hand, this formula gives us a way to solve for n hat. So don't forget, we have all this wonderful vector algebra at our disposal. We can subtract at t hat off both sides. And once again, the acceleration, the unit tangent, and the whoops, there's an n hat there yet. And the t hat, these are typically easy to find. And then an, remember, is the product of 2 magnitudes, which means it's always positive. So we can go ahead and divide by the an. And this, at least when I went through the answer key on the take-home, this is how I found the n hat, as opposed to trying to brute force my way through those derivatives. Okay. All right. Now let's talk about some other formulas for curvature here. Welcome in. So from this formula, we can replace this, and we can get to this formula with curvature. Once again, going through the decomposition equation, taking cross products and all that other stuff. So this is usually the formula students will use to get to the curvature, because once again, t hat prime can be a bit of a pain, especially on the take-home. You're going to have probably v cross a anyway at some point for whatever, but this would be the formula you use. And once again, it comes from looking at the formulas we have for t hat prime. You can get those to work out there for that. Okay, so I'd recommend that one. And you can go, if you have a plane curve, I think this is, did we talk about this formula? I think this is where we ended last time, right? We got up to this formula, and we were going to talk about this today. because this will help us figure out like what curvature is actually trying to do. I mean, I think you can see the definition is we're trying to measure how curvy something is. But what's that actually give us? So let's say we've got a plane curve. Let's say it's of the form y equals f of x. And remember, you can get a cheap parameterization for this. If you let x be t, then y would be f of t. That's the cheap parameterization. And once again, as a reminder, I did upload that parametric tricks of the trade handout I typically give in Calc 2. I updated it for Calc 3. But you can get your vector valued function r of t to look like t comma f of t. And if you want to use this formula for curvature, notice we're taking a cross product. Okay. So what do we need for cross products? Can you technically take the cross product of 2D vectors? So in other words, if I want to use this formula here, right? I mean, I could find my velocity and acceleration, but technically, how would I take a cross product of those two vectors if they're not three-dimensional? What do we do for that? Yeah, we set the z as 0. Very good. So we can go through this now and just say, okay, yeah, it's a two-dimensional trajectory, but we can think of the xy plane as living in xyz space. So we'll just take the derivative here. So to get velocity, I take the derivative. The derivative of t is 1. The derivative of f of t is f prime of t. And then what would the acceleration be? I take the derivative again, what would I get? Yep. 0, f double prime of t, 0. Good. So now we'll go ahead and take our v cross a. And once again, we'll use determinants here to help us with that. So 1, f prime of t, 0, 0, f double prime of t, 0. And it's good that we have a lot of zeros in there because that'll make our calculations a little easier. So let's look at the I component. Ignore the row and column the I hat's in, and guess what? Everything zeroes out. And that should be expected, right? We should get, if we're taking two vectors in the plane and we're taking their cross product, that cross product should live just along the z-axis. Once again, ignore the column that j is in. We get a bunch of zeros there. So all the interesting stuff is going to happen here in the k. If I wipe out the row and column the k is in, I'm just getting f double prime minus 0. So there's the f double prime of t. And so the magnitude of that would be the magnitude of the vector 0, 0, f double prime. If you square the components, add them up, and take the square root, you get the square root of f double prime squared, which would be the absolute value of f double prime. So that cross product falls out quickly. And if I look at the magnitude of v, that's the square root of 1 plus f prime squared. So that means that the magnitude of v cubed would be all of this cubed. So it would be 1 plus f prime of t squared. I can write that as 1 plus f prime of t squared to the 1/2. So I would be taking this to the 1/2 cubed, that's the 3/2. And that's where we get that formula for curvature of a plane curve. So there we go. And then we just ship back in x for t. Now, does it really matter if we have y as a function of x or if we have like x as a function of y? Is that going to really matter here? That's something I ask you on the take home, because it works just as well if you have a function of y. It's the same curvature. So the question is, what does curvature mean? Okay, like if I say the curvature is like 5, so what? All right. Well, we have what's called the radius of curvature. So the radius of curvature is defined to be 1 over the curvature. So it's an inverse relationship. The higher the curvature, the smaller the radius of curvature. Now, when you hear the word radius, what do you instantly think of? Yeah, circle. So what's that all about? Well, let's think about, let's say you've got like a curvy thing. And this is where I really miss the first book we had when I came to Lakeland. The first book we taught out of in Calc 3 was a book by Larson. And in the edition we started, now this was, back in like 2000 or something. So this was a long time ago. This is how they described the circle of curvature. So, like in Calc 1, the whole concept, I know Adam had me for Calc 1, but the phrase local linearity comes up at least, 3,000 times in Calc 1 and Calc 2 when I teach those classes, because that's the whole idea of derivative and tangent line. So, in Calc 1, you pick a curve, it may look curvy, but if the function is differentiable and you zoom in, the curve resembles a line, and that line is a tangent line. So that's the local linearity. Well, the circle of curvature is sort of the best fit circle near the point. And in the Larson book we started with, it said, imagine taking, or the circle of curvature is the circle that's, quote, and this was the verb they used, snuggles. That snuggles up against the curve on the concave side. So the word snuggles was in a math textbook. And I've been on a quest to find it. I don't know what happened to my Larson book. I think I gave it to a student because they were going to use it somewhere else and we weren't using it anymore. But in that edition of Larson, so just imagine this circle snuggling in, all right? And the radius of that circle is your radius of curvature, okay? So if you think about it, the curvier something is, the sharper the turn, that would be the smaller the radius of curvature. So do you see how those are inverse ideas? A high curvature, a shorter radius of curvature, that's a tighter curve because we have a smaller circle. No, it can actually cross through, just like tangent lines can cross through. But locally, if you zoom in tight enough, it's gonna resemble that. Yeah, because you can have, circles of curvature can cross through. So here we go. Kind of like like if the curve's flat enough, it'll cross through like that. But okay, so like how would you find the circle of curvature, right? Because that's what's on your take home. Here's what you do: you get your point, you get your curvature, and then you get your radius of curvature. And now you go back to what you know about circles, right? If this is going to be a point on the circle, so then you're going to have to go figure out the center of the circle. So the circle equation would be x minus h squared plus y minus k squared You know what? Let's not use h and k because I don't want you to confuse k with kappa. Let's use the classic x naught y naught is equal to r squared. So in this particular case, the radius would be the radius of curvature, which you can get. The x naught, y naught, this is called the center of curvature. And the question is, how the heck would we get to the center of curvature? Well, what do we know? We can get the unit tangent vector here, right? Exactly, n hat, very good. So we can get the principal normal vector n hat, which, remember, on the take-home, this is happening in 2 dimensions. So you can do that shortcut, two-dimensional shortcut. And so how far do you go down here? Well, you go down the radius of curvature, n hats, to get to the terminal point. So here's what you would do. Here would be the methodology. So step 1, get your curvature. And you can get your curvature by doing this, right? Oh my goodness, if I could just... There's all kinds of neat questions you can ask about curvature, but so this semester we're going to find the circle of curvature and graph it. So that's how you get your curvature. You get it there, and you plug in whatever x value you're at, or whatever y value you're at. You plug that in. Then you get your radius of curvature. Okay. And then you would get your t hat, which would give you your n hat. And then you look at the vector n hat times rk. And then what you'd have to do is you'd have to start that vector at the point you care about and then find the terminal point. And that's going to be your center of curvature. So once you get your center and your radius, you're good to go. All right? So what I like about this problem is, if you think about it, this ties a lot of the basic vector stuff together with this stuff we're working on here at the end. All right? Because now we have to move the point. And on GeoGebra, you can, I've showed you how you can translate the point, so you can get a nice picture with all this stuff on one nice little picture. Okay, so we can cheap out on this one. This is a more basic example. Find the circle of curvature of the graph f of x equals x squared at 0, 0. So step 1 would be to find the curvature. We have a plane curve, y equals f of x. I keep doing magnitudes there. So f of x is x squared. So what's f prime of x? Two x. And what's f double prime of x? 2. So I feed that into my curvature formula. I get the absolute value of 2, which is 2, divided by 1 plus f prime squared to the 3/2. Now this is a function of x. What x value am I at here, folks? 0. The curvature at 0 would just be 2. Any questions on using the formula to get the curvature formula, or then plugging the point in to get the actual curvature at that point? We good with that? All right, that was step 1. We found the curvature. Step 2, we find the radius of curvature, which is just reciprocal of the curvature. So if the curvature is 2, that means the radius of curvature is 1/2. Now step 3, we would find n hat, which would get us t hat, which would give us n hat. Now we can kind of sort of cheap out here because we know what it should be. Here's our parabola. Right? Oh my goodness. We know that the tangent here is what? We're at the point 0, 0. You follow? And what's the tangent line at 0, 0? Yeah, very good. The x-axis. This is we actually did this in Calc 1 yesterday. Okay, so if that's the tangent, then the normal vector is going to be what? Remember, normal vector points towards the concave side of the curve, so the normal vector is going to be. Yep, perfect. That's our n hat. Now, on your take home, you're going to actually have to go through and get a different n hat. You won't be able to get it by inspection, right, by looking at it. Now we just make, so rk n hat would be 1/2 j hat. So 0, 1/2. And so if I start at 0, 0 and move up, once again, that's just going to get me at 0, 1/2. So that's the center of curvature. So my circle of curvature would be x minus 0 squared plus y minus 1/2 squared is equal to the radius of curvature 1/2 squared. So this is a very basic example that just illustrates the process, and on the take-home you get to go and look at this. But let's fire up GeoGebra here, and we can observe this. Any questions on how we got to the center of curvature? We start at the graph and we move up rk n hat to get to the terminal point, and that's our center of curvature. And so now we can observe the snuggling. Where did my GeoGebra go? It wasn't open. All right, hopefully this won't kill everything. Okay, so we can just stick in 2 dimensions. So we're going to put the old y equals x squared in there, and now we're going to put in the circle of curvature. It was x minus 0, so x squared plus y minus 1/2 squared equals 1/4. Boom, there it is. And now if we zoom in, can you observe the snuggling? Do you see what we mean here? It's the best fit circle. So it's just snuggling, it's just nestling its way right in there, right? You know, just imagine little puppies snuggling into their mom. All right, torsion. So we talked about the osculating plane. Let's go back to the TMB frame. Up here it is. Okay. So remember, the osculating plane is the plane of motion. It's the plane determined by t and n. Okay. So that curve lives in the tn plane. Okay. In the osculating plane. B is the vector that's normal to it. So you can think of B as being the direction of the plane. So if I want to figure out like how that plane is twisting through space, we can measure that twisting by looking at the derivative of B hat. Does that make sense? So you got this right-handed system. The plane lives in the TN plane, and so B is going to tell how the direction of the plane. So we look at how that changes with time. And so if you take the derivative of B hat with respect to t, that's your product rule working there. All right. Now if you remember, what happens? N hat was defined to be t hat prime over the magnitude of t hat prime. So n hat is parallel to t hat prime. And what happens when you take the cross product of parallel vectors? They zero out. Okay, so you kind of see why that one problem was on your take home last time. It kind of goes through this sort of argument. So that puts b hat here. And so what do we know? Since it's a cross product, it's going to be orthogonal to t hat. And it's going to be orthogonal to b hat because b hat is a unit vector. So since b hat's a unit vector, it's orthogonal to its derivative. But this says it's also orthogonal to t hat. So that means that, we've got these three directions here that are, whatever b hat prime is, it's orthogonal to b hat and t hat. That means it has to live along n hat. Does that make sense? If you're orthogonal to b and t, you've got to be somewhere along here. And so we switch back to the arc length parameter because that's the neutral parameter, and this is how we define the torsion. And the negative sign there is for convention. But the torsion measures the twistiness of the curve. All right. And so this is how we define torsion. If we take the magnitude of torsion, we get to here. And so torsion is defined in the same way that curvature is. Remember, curvature was defined as the rate of change of t hat with respect to s. So how your direction along the curve, the direction you're going, how fast that changes with respect to how far you've gone. Torsion is the analogous thing. It's how much the osculating plane is twisting, how much that plane, the direction of that plane is changing with respect to how far you've gone. So torsion is sort of orthogonal to the plane of motion, whereas the t hat is within the plane of motion. So they're sort of dual things. Now once again, going through any of these things, like going through this, is a bit of a nightmare, but you can get torsion this way. And so this would be the formula I recommend for torsion on your take home. Okay. And the reason I have you do the torsion is because the curve I picked for you on the take home has a nice property about its torsion. So here's example 10. You can go through that. Now this would be a great project because I want to have a few minutes and talk about the take home. This would be a great project for you folks. If this kind of thing piques your interest, the Frenet-Serre equations, these are big. These are used to study things as small as molecular motion and as large as satellites in space. So that would be a great project if you're interested in that, deriving them and then looking at where they're used.